Welcome to DriverDTrains. Thanks for stopping by. I'm your host, DriverD. Our conductor and brakeman, Scratchy-C, is taking the day off. Recently, I completed a new series of videos on DCC-EX in 2025, featuring the EX-CSB1 Express and more. In this video, we'll look at how to assemble a WiTController to use with DCC-EX to control our trains. Be sure to check this video's description for links to my other videos, as well as the various websites and products I mention here. Also, if you are enjoying the videos, please leave a comment and hit the like button. And if you haven't already, be sure to subscribe to the channel. We're working without a switch list today, so we'll have to make it up as we go along. Assemble a WiTController for DCC-EX. Here's the general plan for today's action. First, we'll learn about what the WiTController is and what it can do. Then we'll order the necessary parts to assemble a prototype WiTController on our workbench. After that, we'll install the WiTController software and configure some basic settings in the code. Finally, we'll look at some options for assembling our completed WiTController. Now that we have a plan, let's get started. Assemble a WiTController for DCC-EX. Part 1. Introducing the WiTController. The WiTController, or WiTController if you prefer, is an open-source wireless throttle and controller that we can use to control our trains and layouts. The WiTController works with DCC-EX, JMRI, or any other system that features a Y-throttle server. We can use the WiTController to independently control multiple locomotives and consists, set turnouts, and dispatch locomotives on routes. And because the WiTController is an open-source project, we can customize both the hardware and software to suit our needs. The WiTController was created by Peter Akers from Queensland, Australia. Peter has also done development work on the Engine Driver app and the Y-throttle protocol code library. You can see more of Peter's work, along with videos of the Railway Modelers Club of Queensland, here on Peter's YouTube channel. All the information about the WiTController, including links to download the software and examples of completed controllers, is available on Peter's GitHub page. I'll include a link in this video's description. We'll go ahead and download the software now so that we have a copy ready to go on our computer. The download package includes images with a number of possible configurations for the WiTController, but we can also come up with our own configuration with just the features we want. The basic WiTController features a push-button keypad to select our locomotives and decoder functions, an encoder knob or potentiometer to control our locomotive's speed and direction, and an OLED display to show all the details for our trains and layout, as well as menus to control all the WiTController functions. In addition, we can add up to 11 additional buttons to the controller to perform additional functions. The WiTController runs on an ESP32 development board and can be powered from a rechargeable battery. We will install the WiTController software onto the ESP32 using the Arduino IDE. I will assume that you are already familiar with how to use the Arduino IDE with an ESP32. If not, be sure to see my video number 8C, Configure DCC-EX EX-CSB1 with Arduino IDE. We can install the WiTController hardware into any kind of suitably sized, non-metallic project box, or print out a 3D case for it. Again, there are numerous images of sample cases included in the WiTController software download. And while most users think of the WiTController as a handheld device, we can also use it as a tabletop controller or mount it to the layout benchwork. In this video, we'll look at the basic hardware options for the WiTController and all the necessary parts. Look at how to prototype the WiTController on a breadboard, and then look at an example of a finished controller assembled into a 3D printed case. In my next video, we'll look at how to use the WiTController to run our trains and control our layouts. Part 2. Purchasing the necessary hardware. The WiTController is an open-source DIY project based on an ESP32 microcontroller. To assemble a WiTController, we will need to obtain a number of different parts. There is no one-size-fits-all version of the WiTController, so the parts we need will depend on what specific features we want our WiTController to have. We can choose what size screen we want, how many keys we want on the keypad, whether we want to use a potentiometer knob or a rotary encoder, if we want to use a battery, and whether or not we want any additional buttons beyond those on the keypad. Regardless of what configuration we choose, we are also going to need to do some wiring and soldering to assemble all these parts, so having the necessary soldering supplies will be a must. We'll also need some jumper wires, circuit board header pins, and a switch and some resistors for the battery. A solderless breadboard for testing is also helpful, but not necessary. Finally, we will need to decide what kind of case we want to put our WiTController in. We can use a simple project box, make something custom out of wood or plastic, or 3D print something. For this video, we will be using a 1.3-inch and a 2.4-inch OLED display, a 16-key number pad, and a rotary encoder. We'll start by assembling and testing everything on a breadboard. Then we'll add a battery and put it all together in a 3D printed case. Here is a list of the parts we'll need. First, we'll need the ESP32. The specific version of the ESP32 that we are using is called the WeMOS Lite V1.0.0 ESP32 development board. This board has 13 pins on each side and a connector to attach a lithium polymer LiPo battery. A slightly larger version, called the WeMOS Lowlin, with 16 pins on each side, is also available. The board is also available with either a USB-C or a micro USB connector. I recommend using a board with a USB-C connector if possible. It's also usually cheaper to buy several ESP32 dev boards at a time. There are a number of different manufacturers that make these boards, so we can find them under many different names. I purchased a 4-pack of this Al-Anon branded board with a USB-C connector for $16 on Amazon. I'll include links for all the parts in this video's description. The next item we will need is a keypad. These are typically available in either a 3x4 matrix with 12 keys or a 4x4 matrix with 16 keys. Unfortunately, there are not a lot of viable options for these, and the most common one is, to put it kindly, junk or rubbish. Dozens of different vendors sell these keypads, but they are all the same. The circuit board traces and solder points are laid on top of Bakelite, which is just resin-soaked paper, and held in place by melting the plastic standoffs on the keyboard frame. There are no through-hole connectors. Let's just say that the keypads are not very durable. There are other push-button matrix button pads available, but nothing really suitable for our purpose unless we want to make our own keycaps and frame. We will probably ruin one or two trying to solder wires to them, so I suggest purchasing a few. A single 16-key keypad costs about $8 on Amazon, but I purchased this 4-pack for $14. The next item on our list is a rotary encoder. We will use an encoder mounted on a development board module known as a KY-040. It is also possible to use a bare EC11 rotary encoder or a potentiometer volume knob by adjusting settings in the WiTController software configuration file. We'll also need a 128x64 OLED I2C display. I discussed these displays at length in my video number 8E, Add a Second Display to DCC-EX. They come in various sizes from just under 1 inch to 2.42 inches. In this video, we'll use a 1.3-inch OLED for our prototyping and one of the larger 2.4-inch ones for our final assembly. In order to use our WiTController without powering it from a USB port, we'll also need a 3.7 volt LiPo battery with a 2.0mm JST connector. These come in various shapes and sizes, and what size we choose will depend on how much room we have in the case that we mount the WiTController in. I originally purchased a 500 mAh battery, but found that it only lasted for about an hour. I plan to upgrade to a 1200 mAh battery next. Note that there is no agreed upon standard for which pin in the connector is the positive voltage and which is the negative, so we will need to carefully compare the polarity of our battery to the polarity of the ESP32 development board and make sure that they are the same, or else carefully remove and reverse the wires on the battery connector. We could also cut and swap the red and black wires on the battery, or purchase parts to make an adapter cable to reverse the polarity. Regardless of which method we use, we'll need to make sure that we don't accidentally short out the battery wires. To prevent the battery from draining when we're not using the WiTController, we'll want some kind of power switch, and in order to show the battery percentage remaining on the display, we'll need a couple of 47 k-ohm resistors to make a voltage divider. We'll also need some jumper wires, and possibly some right-angle header pins. Finally, although we won't be adding any extra buttons to the WiTController in this video, if and when we do want to add any extra buttons, we'll need those, and possibly some 10 k-ohm pull-up resistors. Again, I'll include a list of all the necessary parts in this video's description. Part 3. Assembling the hardware prototype. Once we have obtained all the necessary components, we can begin to assemble our WiTController. For this video, we will do the initial assembly on a breadboard, but we could just as easily do it on our workbench without the breadboard. Pre-assembling the WiTController will help us to see how all the parts fit together before we install them in a case. To begin, we'll need to solder header pins to the ESP32 and the OLED display. On the breadboard, I've used the straight pins that came with the boards, but for the final assembly, we might want to use right-angle pins instead. Note that I do not recommend using header pins on the keypad. The circuit traces on the Bakelite board are very flimsy, and a little pressure on the pins will easily break the traces off the board. Ask me how I know. There's a reason I bought 4. For this video, I've soldered jumper wires directly to the keypad. Note that you may be able to get away with using header pins if you're gentle. Right-angle pins, as seen in this example by Sayarev, may work better than straight pins, but we'll still want to be gentle. We can find wiring diagrams for various configurations of the WiTController in the zip file we downloaded and on the WiTController GitHub page. We don't have to worry about finding an exact match for our configuration. We can refer to multiple diagrams for the components we're using. We'll start with this wiring diagram for the 16-key 4x4 number pad. We'll ignore the 6 optional buttons since we're not using them in this video. We'll lay out the ESP32, the OLED display, and the rotary encoder on the breadboard. Since we've soldered jumper wires directly to the keypad, we won't be placing it on the breadboard. If you've never used a solderless breadboard before, it's very simple, but you need to understand how the board is laid out. The middle portion of the breadboard is divided into 2 halves with a channel running between them. On either side of this are 2 smaller strips marked with plus and minus and colored with blue and red lines. These are the power rails. If we lay the breadboard out horizontally, we'll see that the center portion of the breadboard has many numbered columns with 5 pinholes on either side of the central channel. These are lettered from A to E on one side and F to J on the other. In each column, the lettered pinholes on the same side of the central channel are all connected together. So, for example, pins A1, B1, C1, D1, and E1 are all connected to each other, and pins F1, G1, H1, I1, and J1 are all connected to each other, but these 2 sets of pins are not connected to each other. Likewise, the 2 power rails are also not connected to each other. Therefore, when we lay out the ESP32 on the breadboard, we'll need to orient it in the same direction as the breadboard and have the pins on one side of the ESP32 board be on one side of the central channel, and the pins on the other side of the ESP32 board be on the other side of the channel. We can then plug our jumper wires into the holes next to the pins we want to connect to. When we lay out the OLED display, we'll need to be sure to also orient it such that each pin is in a different numbered column. The same goes for the rotary encoder. The power rails on either side of the breadboard are not connected to the central section. Instead, on each power rail, all the plus pins are connected together and all the minus pins are connected together down the entire length of the rail. These rails provide a common source of plus VCC and ground to the components on the breadboard, so long as we connect the components to the rails using jumper wires. We'll connect the VCC and ground pins on the ESP32, OLED, and rotary encoder to one of the plus and minus pins on one of the power rails. We'll need to make sure they all connect to the same rail because the two rails are not connected to each other. Now we'll use jumper wires to connect all the components to the ESP32 pins as shown in the wiring diagram. There are lots of wires, 8 on the keypad, 4 on the OLED, and 5 on the rotary encoder, so we'll want to pay attention and double check our work. We are now ready to install the software. Part 4. Installing the WiTController software. Now that we've assembled the WiTController hardware prototype, let's install the WiTController software code on the ESP32. Again, we'll use the Arduino IDE for this, and I will assume that you have already installed the ESP32 boards package in the Arduino IDE Boards Manager, as I described in my previous videos. We'll find the WiTController zip file we downloaded from GitHub, and double-click on it to extract its contents. We'll drag the WiTController main folder to a convenient location on our computer and rename it to be just WiTController. Inside the WiTController folder, we'll make a duplicate copy of the config_network_example.h file and just call it config_network.h. We'll do the same for the config_buttons_example.h file. Now we can open the WiTController.ino sketch. In the Arduino IDE, we'll check the board selection drop-down menu to see which ports are currently active. Then we'll use a USB-C cable to connect our WiTController's ESP32 to one of the USB ports on our computer. We'll check the board selection drop-down menu again and select the new port that just showed up in the menu. Then we'll select ESP32 Dev Module from the list of boards. Finally, we'll use the Tools menu and set the download speed to 115/200. We now need to install 4 libraries using the Arduino IDE Library Manager. These libraries are listed near the top of the WiTController.ino sketch. First is the Keypad Library by Mark Stanley and Alexander Brevig for the Matrix keypad. Next is the U8G2 library by Oliver, which is for the OLED display. After that is the Y-Throttle Protocol library by Peter Akers, David Zune, and Luca Dentella. Peter's is the newer version of the library. Finally, we need the AI ESP32 rotary encoder library by Igor Antolik. Once we have installed all these libraries and selected the board and port in the Arduino IDE, we can check the code to make sure it compiles by clicking on the round button with the check mark in the upper left corner of the IDE window. We could now upload the WiTController code to the ESP32 if we wanted, but let's enter our Wi-Fi information in the config_network.h sketch first, so we don't have to try to do it manually, one letter at a time, using the rotary encoder on the WiTController. We'll go to the config_network.h sketch, and near the top, replace the network 1 and password 1 with our Wi-Fi network name and password. We can store up to 4 Wi-Fi network names and passwords if we plan to use our WiTController on multiple layouts or on different networks. Also, because we are using a 4x4 keypad for this video, we'll need to configure the WiTController code to use that extra column of buttons. We can do this in the config_buttons.h sketch by uncommenting lines 244 to 248 in the code. Before we go on, we'll want to make sure that our DCC-EX command station is booted up and running, or that we have JMRI running with an active WiThrottle server. Now we can upload the code to the ESP32. We can see the progress in the output window as the IDE compiles the code and uploads it to the ESP32. Once the upload is complete, the ESP32 will reboot and we should see a message on its OLED display. We can also open the IDE serial monitor and should see messages indicating that the WiTController is working. Note that by default, the WiTController is configured for OLED displays with an I2C address of 0x3c or 0x78, which is equal to 0x3c times 2 in hexadecimal. If our OLED is using the 0x3d or 0x7a address, we can change the address WiTController uses by uncommenting line 1639 in the WiTController.ino sketch and entering our OLED's I2C address. If you would like more information about configuring OLED displays, see my video number 8E, Add a Second Display to DCC-EX. Now, if we look at the WiTController's OLED display, after a brief message indicating that it is browsing for SSIDs, we should see a numbered list of available Wi-Fi networks. We'll select the Wi-Fi network that our command station is connected to, and, assuming we entered the password in the config_network.h sketch, the WiTController will connect and start looking for available WiThrottle servers. Once it finds a WiThrottle server, it will connect and display a message with the name of the server on the OLED display. We can then press the asterisk key on the keypad to open the main WiTController menu, where we can select our locomotives and start running our trains. We'll look further at how to use the WiTController to control our trains and layouts in the next video. Before we move on, however, there are a couple of configuration settings we may want to adjust in the WiTController code. If the text is cut off on one side of the OLED display, we can select a different screen definition in the config_buttons.h sketch, starting at line 165. For the 1.3-inch OLED in our prototype, we will uncomment the code on line 180. We can also change the direction of the rotary encoder so that clockwise means increase locomotive speed by uncommenting the code on line 18 and changing the encoder rotation clockwise is increase speed from false to true. On line 38, we can also adjust the sensitivity of the encoder by changing the definition for rotary encoder steps. I found that 4 worked best for the encoders I used. And we can uncomment line 113 and change the speed step definition to 1. Finally, we can change what the keyboard buttons do and the corresponding text displayed on the OLED screen by changing the keypad function definitions and display names starting at line 55. I've configured my keypad to operate 10 locomotive functions: speed up and speed down the throttle, activate the emergency stop function, and switch to the next locomotive throttle. There are many more configuration settings that are explained in the code, but the only ones we'll touch on today are the battery test settings. We should only change these when we are ready to run the WiTController with a battery. If we add a battery and voltage divider resistors when we assemble the final version of our WiTController, we can set the definition for Use Battery Test and Use Battery Percent as well as Icon to True, so that we can see the battery percentage remaining on the OLED display. Part 5. Assembling our WiTController. Now that we have tested and configured our prototype on the workbench, we can decide what we want our finished WiTController to look like. We can look at the examples provided in the WiTController code, as well as look online for other examples for inspiration. We can also decide what other features we want to add, including the battery and any additional buttons. We can refer to the various wiring diagrams included with the WiTController software to see how those need to be wired up, and we can find additional information in the README file. Note that if we want to add a switch for the battery, we should add it to the positive lead of the battery and between the battery and the voltage divider resistors if we use them. For my own controller, I wanted something that was as small and light as possible while still using the 2.4-inch OLED display and a 4x4 keypad. I placed the keypad directly above the ESP32 dev board to keep that wiring as short and neat as possible. I placed the battery under the display and away from the encoder so that the encoder wouldn't press down on it. I tried to keep the wiring to a minimum and tuck the resistors for the battery voltage divider in where I could. After adding shrink wrap to the resistors, I was able to tuck the ends of their wire leads into the back of the jumper wire connectors on the microcontroller board without needing to solder them. I went through several iterations for the design of the case and plan to make a few more tweaks to accommodate a larger battery and move the USB-C port closer to the edge of the controller. I am also hoping to replace the tall rotary encoder with a click wheel style encoder that also features 4 directional buttons. I'll include a link in this video's description where you can find the 3D STL files for the different versions of the case shown here. What's next? Using the WiTController to control our trains. In my next video, we'll look further at how to use the WiTController to control our trains and consists, operate turnouts, and set routes on our layouts. Be sure to subscribe to the channel so you don't miss any upcoming videos, and check this video's description for links to my other videos, including my video series on assembling a DCC-EX command station and my series on using JMRI's Decoder Pro app to control our trains. We've moved some cars around today and cleared the siding, so let's head back to the yard and call it a night. I'm sure there will be something else for us to do tomorrow.
Yeah, come on down to the BN, let's throw light over. Signal indication BN, thanks.
Until then, thanks for watching. Well, Scratchy, are you ready to get back to work? Well, okay then, never mind. All aboard!